Good afternoon, everybody, or good evening, good morning, wherever you're watching me from. We're here for Mechanical Laboratory 1, and I hopefully have managed to find a means to record both myself and the lecture slides that's a little bit easier to use than Panopto. You might have observed that to do this I've got a green screen, which is why I can appear in a lovely scene like the one we've got behind us. It also means I could be up the Sears Tower. I can also have videos behind me, which is kind of cool. I'm not going to spend a lot of time messing around with that, not too much anyway. But where this is really useful is that I can have the slides for today's lecture. Oh, and let's pan that down so I've got the top of the screen there properly. The slides for today's lecture, and I can also be talking in front of it. So this is what we're going through today. Now we're going through a bit of the administration of the course. Let me just make sure that's showing up. So we've got to go through some of the administration of the course now that we are online completely. And then we're going into the real topic, which is an introduction to calibration. I think this date might be incorrect by the time this gets uploaded. By the time this is ready to view, it might be tomorrow. It might be Wednesday, which I guess is today if you're on that date. So we're talking about a few things today. Like I say, we've got to talk about the way the course is going to be run from now on. I spoke a little bit about that last week, but I want to keep talking about that today. We're then getting into the meat of this lecture. So we're looking at calibration theory. So firstly, what is calibration? Why do we do it? And then we're going to look at the underlying procedure that takes place every time we perform a calibration. We're going to talk about zeroing a bit more. We've spoken about zeroing a little bit before in class, but we're going to speak about it now in a lot more detail. We're then going to look at transducers, and particularly what ratiometric transducers are. If a transducer is ratiometric, we need to deal with it carefully. Now, most transducers we will use in analog electronics and even in digital electronics will be ratiometric, so we've got to be aware of what that means. And then we're looking at some data reduction of calibration data, and I'm using Python. Now, I've switched over to using Python, and I'm using the Spider IDE. So Spider is the name of the integrated development environment that looks a little bit like MATLAB, which is what helps us to run code, look at variables, and produce plots in the same place. Now, as I've said before, the reason I'm doing this is because MATLAB on the VCL is quite difficult to use. So I don't want to use that. I don't want you guys to have to use it. And it's why I'm showing you alternatives for using a different coding tool for this. If you've got your own copy of MATLAB, you're obviously free to use that as well. Whilst this course is taking a little bit of a step back in terms of all of the technical content, and we're having to think about how to reshuffle things, maybe now, in all this downtime, would be a good idea to learn another programming language or to pick up Python to a slightly better standard. So if you haven't used it before, search online for a good course. And in fact, I'll help you search for one on screen in a moment, or when we get to that point. Have a look at it, see if you can get your head around it. Fundamentally, Python's free, so we can get a copy of the Anaconda distribution, which includes Spider, the IDE. We've got that working on our computer, which is what you'll see me using. Then you guys can copy everything and hopefully actually understand all the commands as we go through them. So let's move on to the administration and the introduction that we're doing today. So we've moved on to pass-fail for this course. Now, all of your courses will have moved that way, I imagine. So this is something completely outside of my control. I can't give you a letter grade for this course unless you're a graduating senior. You've got to petition me and I can give you a proper letter grade for this course. Now, that's quite good for this course because this is a laboratory-based subject and we can't go into the laboratory. So I can use this time to teach you instead the same topics via a mixture of videos, of data, and some interesting homeworks. But fundamentally, I can't teach you all the things that I'm supposed to be, or moreover, I can teach you the things that I'm supposed to teach you, but you can't get the hands-on experience that you guys should be having from your course. So again, this is outside of my control. If you want to discuss this, look on Slack, put something up there. I'm happy to talk about the merits of this as we go forward. It does mean though that it's not effortless to pass this course, okay? So some students will fail. That's just my prediction. This isn't about I think it's a particularly difficult course. I just know that it's going to be troublesome to adapt straight away to online learning because it involves a lot of discipline that you guys might not have practiced so far in your academic careers. You've got to maintain a schedule, and you've got to be following all of the videos that I upload and all of the assignments. So you've got to make sure you go through those. I started the Slack space, which is good. So I'm glad you guys. Let me just make this up a little bit smaller. So I started the Slack space, and I'm glad to see that you guys are using that. I've got one for 304, which is my aero structures course, and one for this course. Now, it's being used a lot in 304 for student questions, which is really useful. So if you have a homework question, which you will do as I start assigning homework as this course goes on, then if you feel comfortable asking that in a public forum, please pop a question on Slack, and that pops up on my computer straight away. I can then look at it, I can reply, and then everyone can see the answer. Okay, you're also free to message me on there privately. That's fine. Just be aware that it might be easier sometimes if you've got a question that you are happy to ask in front of another student, pop it on there on the student to instructor page, and then the answer will be available for others. So let's give you a moment to read that. And what do I mean by this? I'm still determining new homework and assignments for this course. So what we would have had before, or what the previous assignments would have been, we had 3 times large laboratories. Let's spell that correctly. So we'd had 3 large data acquisition experiments, and then you would have had 3 times reports to make. You'd have had a small report, a large report, and a poster report to do as a group. Now, I'm not too keen on the idea of just giving you guys the data and asking you to do the reports, because I feel that only placates my requirement of running a laboratory course. I would rather go more into detail on the theory of measurement, how we reduce data, and then I'll get you guys to go through some sort of dummy data acquisition exercises, and we'll talk about good science writing, and I'm going to give Blackboard assignments that require you to understand where, say, science writing has been done well, where science writing has been done poorly. So I will be disseminating how I'm going to pass or fail the students as I go along, but for the time being, the necessary condition for passing this course is watching all the videos and answering all the quizzes in this video, so I can see those data. If you haven't done those, then you're not going to pass this course, okay? So that's the absolute necessary condition. It's not the sufficient condition. The sufficient condition will be determined. That's what I'm going to be looking at in terms of understanding how I'm going to be giving assignments, etc. for this course. So also you need to watch the video via the link that I give you in Slack. So you've got to give your name and your IIT email at the beginning. So this is so I can tally your quiz answers into the responses I get, and I can see who's watched the video, who's watched to the end. So you've got to watch it on your own account. Obviously, if you weren't all on lockdown, you guys could claim that we're all watching it together under one ID. Thankfully, I know that you guys aren't all watching things together, so you've got to watch it on your own, and you've got to, at the very minimum, go through all of those quiz answers. So that's the administration side of things over. Again, if there are questions on there, please feel free to put them on Slack, and then I'll answer them in a public forum. So we're talking about calibration. Why do we calibrate, and fundamentally, what is it? So to perform measurements of anything, if we are taking measurements in a scientific and an engineering setting, we need to know both the accuracy and the precision of our measurement devices. So let's just remind ourselves what these words mean. Accuracy is how close we are to the true value. Okay, so this is effectively how close we are to the bullseye of a target. So that's accuracy. Precision, on the other hand, precision is the smallest change that we can reliably measure, or how close our measurements are to one another. All right, put in brackets here, smallest change. So you will have seen different diagrams for this, maybe back in high school or in other science subjects, but we can quantify our accuracy and our precision. Well, not quantify, we can have a qualitative representation of the two. So if I've got a target and I'm trying to hit the center, again, close to drawing another slightly crude drawing here. We can put accuracy on the vertical axis, and we can put precision on the horizontal axis. So if we have low accuracy and low precision, that means that none of our shots are particularly close to the bullseye, and they're all spread quite far apart. If we have low accuracy and we've got high precision, then actually we have quite good grouping effectively in our measurements. They're all pretty close around one another, but they're still quite far away from the center of the target. Over here, we can look at high accuracy, low precision. We can have a good spread around the bullseye, but effectively, if we took the average of them all, they're all pretty centered around the actual bullseye. And then if we have high accuracy and high precision, that means we've got all of our readings around that center point. Okay, so just remember the difference between these two words, what accuracy is and what precision is, because in the writing exercises that we're going to be doing, if you use one of these words, accuracy or precision, it's got to be in the correct sense. There's a real tendency in spoken English and often in technical writing to use accuracy where we mean precision. Now, this idea of accuracy, it's actually much harder to measure than precision, because for accuracy, what do we need? And I'm going to try and put a quiz up here, we'll see if that works. For accuracy, we obviously need to know what the actual true value is. So it's this idea of this true value, we need to know that. So that's quite difficult for us to measure, often because we're trying to determine how good a particular measurement device is at measuring something. So if we knew what it was in the first place, then we wouldn't be measuring it. So that's why accuracy is sometimes more difficult to quantify. We tend to mean precision when we're talking about these two. Another reason why we tend to mean precision, and why precision tends to be more important, if we are, say, looking at comparative measurements, which is often what we're doing as engineers. So comparative measurements, we tend to want really great precision. We don't care quite so much about accuracy. So if we've got, say, two configurations that we're comparing, we can then say A is better than B. If we've got, let's move that up so you guys can see it. We can say that if we have two configurations, A is better than B, because we can measure that A performs better than configuration B. We don't particularly care about the true value of, in this example, A or B. We just care that we can reliably say that one is bigger than the other. And we can appreciate that over on this sort of measurement device over here, if we had high precision, as long as we were reliably getting answers that are pretty close to each other, as long as it doesn't matter how far they are away from the bullseye, then what we care about for those sorts of measurement is precision and not so much accuracy. Other purposes is where we really care about accuracy. Let's think about where we might care about that. Accuracy is when we've got any, say, standards to which we need to adhere. So let's say environmental standards. So say if we're producing a vehicle that has stringent emission standards, then we need to be certain that our emissions that we're measuring are accurate compared to a certain standard. It doesn't matter whether we can just say that car A that we produce is more efficient than car B. What we need to know is about the actual accuracy of those measurements. And again, we can think about more trivial examples. If you've got a weighing scales in a greengrocer's, you'd care about both accuracy and precision there, but you certainly would care about accuracy. So this is just to give you guys an overview of these two different words. When you're using one of these words, be careful which one you use, because often there's a tendency to just say accuracy when we mean precision. So that idea of needing to know the correct answer, this is this idea of accuracy. So we'll highlight this in red, correct answer. And this is where we have calibration standards. So we don't necessarily know what the true value of anything is before we do an experiment. So we've got different sets of standards we can use. We can have national standards. Now these are devices that are maintained within a particular country for the measurement of a particular set of of quantities. So in America, it's NIST, I think. I'll Google that and provide a link later. They're responsible for determining how certain quantities are to be measured. Now we can, from those national standards, calibrate other transducers, other measurement devices, and then compare our measurement devices against those. When you're performing real-world laboratory experiments, we need to be able to prove that our measurement devices are traceable all the way back to these national standards. So it's this idea that's not showing up. There we go. So it's this idea that we've got a measurement device, we've prepared it against another transducer, perhaps that was calibrated on a certain date, and this was traceable all the way back to national standards because it was performed by another verified institution. Let's move this up here. So once we've got a good calibration for whatever device we're using, we've also then got an idea of the certainty of any measurements we take. So we're going to talk more about uncertainty and how we quantify that in the next lecture. But everything comes back to the device that we're using to measure it. So if we use a particular, we'll say if you were measuring your weight, or your mass I should say, first thing in the morning in your bathroom, if you know that the device is only precise to say 0.1 kilograms or 0.2 pounds, then that tells you actually, well, you shouldn't really observe any trends in your weight you shouldn't pay credence to any trends in your weight that are below that threshold. Very similarly, if we're looking at transducer calibrations, we've got an idea about how much they might fluctuate within a certain measurement period or for a certain measurement amount, and we then know that we shouldn't trust any fluctuations below those bounds. So what is calibration? Let's go through the whole underlying process of calibration. It's always a two-stage process. We have got some sort of device that we know that when we do something to it, we have an output. So we can think about different calibration devices. We've got electric devices. So we've got weighing scales, we've got pressure transducers, we've got force transducers, and we've got purely analog non-electric devices. So we can have a spring with a needle on it. We can have an analog weighing scale. There is some relationship between the measurement device's input and its output. So let's think about what these terms mean. The input to these devices is what we call the quantity of interest. So for a pressure transducer, this would be pressure, which we measure in pascals or newtons per square meter. The output from a pressure transducer might be volts, or it might be amps. Depends what sort of transducer we've got. We've got to work out, if we change the pressure going into it, how does the output vary? If we've got, say, an analog measurement, let's say we're looking at, an analog non-electric device. Let's have a look, say, mass. If we're looking at a weighing scale, we'd have a mass input, which we would measure in kilograms, and the output for this one would be, say, needle movement. Which is then a displacement. Which I'll give the symbol S, and that's actually then measured in meters. So we think about, we've got these measurement devices, we've got the input is what we care about, and the output is actually something that we're going to end up reading at the end of the day, which maybe sounds sort of back to front in terms of how we use the device, but we've got to think about how the device works. Its input is what we care about, and the output is this quantity that's somehow related to it. Once we've got those two, we then develop the inverse relationship. So say if I have my box up here, this is a pressure transducer, and I've got the input, and I've got my output coming out. So my input is in pascals going in, and my output is volts coming out. That doesn't help me in terms of getting any data out from my measurement. If I've got an experiment, I would say want to understand what the pressure readings are. So what I'll be looking at the volts, and I then want to convert them to pascals again. So what I then do is I then want to determine the inverse relationship. So we're going to say that our input is in volts, and our output is going to give us pascals. And we can then just call this some other name in here. I'll call this K. This is then our calibration. Call it whatever letter you want there, but this is then our calibration that we've got for this device. So remember, it's a two-stage process. First off, we determine the relationship between the thing we care about and what the transducer or the measurement device actually gives out, and then we look at working out the other way around, which is what we're really going to end up using in an experiment. So it's super simple theory. We've got some sort of box. We tend to, as engineers, treat all of our devices as black boxes with inputs and outputs. And actually, it is a simple process to do. There's not many steps, but there are many ways that we can mess it up. There are many ways that we can cause confusion and end up with an incorrect calibration. And if we've messed up our calibration, we can then have real issues because our experiment then produces rubbish data. So we've got to be really careful about zeroing. Zeroing is tremendously important, and there's a related topic to this, which I'm going to talk a little bit about. Maybe not today, maybe next lecture, which is offset removal. Okay, these are both effectively the same thing, but we need to be careful with these when we firstly do a calibration and then when we use that calibration to produce data. So incorrect zeroing can really mess us up, and I'll do a visual example of that in the next slide. Other one is this failure to recognize ratiometric effects. Now, this is something I didn't really learn about until I started my job at the Aircraft Research Association. So this is not typically taught at the undergraduate level, but it's, or it certainly isn't in a lot of courses, but it's a really important measurement effect in any transducer that we're going to be using, and we have to be really careful with it. So we're going to introduce this word ratiometric in a little while, and we're going to talk about what it means. So I've worked with graduate engineers who don't understand this and have taken poor data, and I've had TAs, none of whom are currently on this course, spend a day or so doing a calibration for me, only to have not recorded the input voltage, and thus whole thing's ruined because they didn't understand this idea of ratiometric effects. So this first one, why is zeroing important? Well, let's use an animation to to show what I'm talking about here. So since I don't have the laboratory to work in, I've been trying my best to produce animations that help us understand things. You'll see my Adobe Animate skills are okay, they're not wonderful. But what we've got here, let's say our measurement device is a spring, and we are looking at we've got a pan attached to the end of it, and we've got different masses here. And we've got some sort of graduated device up here. So we can look at this device and we know if we put weights on here, then we would expect the displacement to be down in this direction. So we'll call this direction X. As we add masses to these, we'd expect them to go down. Now, we also know that a spring exhibits Hookean behavior, Hooke's law. So we should have on here, our X is going to be equal to something, which we'll call the stiffness, multiplied by the force that's acting on it. So the force which is acting downwards is mg. So we'd expect this to be some sort of linear relationship. So let's have a look here. Let's say if our thing that we care about on the bottom is mass, and we then have our displacement along the bottom, we would expect our relationship to look like this. This isn't so much about zeroing, it's just another thing to be cognizant of, which is have an idea of what your relationship is for your transducer before you go in and do an experiment. Now let's write that on here. So we should have an idea of what our calibration relationship is before we perform any experiment. And that's useful because if we start taking data points, say if I was performing this experiment and I was applying masses along here and looking at X, which is my displacement, if I started putting these on, I've put one mass on there, second mass on, second mass, second mass, second mass, third mass, fourth mass. This, to me, well, this isn't a linear relationship, is it? We've got some sort of exponential increase here. What's probably happening here is we've got, I've gone beyond the, gone beyond the elastic limit of this device. But fundamentally, if we've got any sort of relationship that is discordant with what we expect, and we can look at this as we're starting a calibration, we can then know, actually, I shouldn't carry on with this experiment, or I should just check to see if I've got a power lead unplugged, if I've got the supply voltage correct, or if I'm maybe saturating my analog to digital converter. So if your data isn't in agreement with the theory, then we stop. We stop the experiment, we investigate what's going on. We see what's happening. And then if it turns out that actually I had the supply voltage incorrect, or I didn't have it plugged in at all, or I maybe had, say if we were looking at this experiment up here, if this is obviously a perfect spring we've got designed here, but what we could have is we could have had some fouling within an internal spring. If you see those behaviors being exhibited in your measurement device, then we stop. We get rid of the data we've taken up to that point and neglect it. We're not going to use it in calibration, and we'll move forward from that point. That's one of the cases where it's fine to just get rid of data if you know that it's bad because you took it poorly. But so we're going to look at zeroing now and why it's important. So we've got our measurement device here. We've got our spring, our Hookean spring. We're going to put our masses on there. So at the very start of the experiment, we've got no mass on our pan. So we could immediately say, okay, well, I know I've got nothing on here, so I can mark my 0 position on here immediately. I can mark my 0, and then what I'll start to do is I'll start taking masses and I'll put them on the pan. And then we see the spring increasing down. I get 1 kilogram, 2 kilogram. This is very handily hit those graduated lines. That shows my animation skills. But we might reach an issue here, and you sometimes will do in experimental procedures where actually, well, what I care about is this device, and I can't get any more masses on this pan. So actually I'm going to take the whole thing off, and I'm going to replace it with a larger pan that I happen to have. And then what's happened? My whole spring has gone upwards, obviously, because the pan weighed something. So where I've gone back to here, this ain't 0. This would then be accordingly -1. So what we've just done here is we've said, okay, well, I was trying to calibrate this device here on its own, but what I was actually doing was calibrating this whole thing coupled together. And we can appreciate that if we're using a transducer in an experiment and we don't pay attention to what the 0 is at the beginning, then we could get the incorrect answer. So we have to be very careful with understanding when we take a 0 and what we do with it. So the 0 that we take at the beginning of our experiment, we take one when the transducer is in what's called a quiescent state. So we take that when our transducer is in this quiescent state, and by quiescent we mean when there's no loading on it. Okay, so we do that, so then we're effectively, we don't subtract it from anything just yet, or we're not going to subtract it in part of our measurements, but what we're going to be building up is some data. So if we're looking at X versus mass here, I would have this small offset in my curve that I got at the bottom. Okay, so this would be, let's call this C. This I've annoyingly called this M here because M is normally the gradient, but we'll just say here that our X displacement is equal to K multiplied by M plus C. So we've got the gradient, and we've got the offset. And this will be effectively, it should be our 0 at the very beginning. Okay, what we'll actually end up with here, this will be the intercept of this straight line that we draw through our data. And I'll talk you through how we do that using Python in a moment. But this is where we've got to be careful with where we take a 0, and just understanding that what we take to be our 0 value isn't necessarily 0 for our calibration, and it almost certainly won't be 0 for our experiment either. Ratiometric transducers next. Okay, so the previous example was a completely physical analog spring, had no power going to it. Now what we tend to use as engineers, we use transducers. So transducer is any device that's capable of taking a quantity of interest and turning it into an electrical change. You'll sometimes see it being abbreviated to TX. So these are usually some sort of voltage, or it could be a current change instead. Ultimately, most of these measurement devices are based around strain gauges. So even if we have a pressure transducer or a force transducer or I can't think of any other transducers off the top of my head. But if we've got these devices, they're often measuring strain and how that changes, and ultimately how resistance changes. Thermocouple is another example that's measuring effectively a change in resistivity of two materials. So all of our devices are somehow relying on the way that its internal conductance changes due to the quantity of interest. So the transducer just takes our inputs and produces our outputs. So our input for this one, if we're looking at, say, a strain gauge, our strain will put axial strain on the left-hand side. The output would be a change in voltage. Now, that explains what a transducer is. It doesn't explain what this word ratiometric means. Now, in order for there to be a strain gauge, let's have a think about how that works. So let's make a simple DC circuit. We'll make a circuit with two resistors, one of which is variable, one of which has got some constant resistance. Hey Poppy. Sorry, my dog is enjoying having me at home. So we've got our variable resistor and we've got our other constant resistor. Okay, we're not going to do a full calculation based upon these two, but you can just think about what's happening. We've got our output voltage and we've got our input voltage to this circuit here. So our variable resistor is our strain gauge. So this is then just a device that when we stretch it or when we contract it, we're changing its length. So when we're changing strain on it, we're then changing its resistance. So R is then a function of the strain on this device. So if we're changing the resistance in this one here, we've got a voltage divider. This means that V out is then a function of strain in this case. But also, V out is a function of the input voltage. So actually, we can get, well, this is still true, but we'll say that it's a function of strain and the input to this circuit. So that's a really important point to get from this sort of experiment. So let's go back to our model over here, this simple black box. We have not just the strain, which we care about for this device, we've also got V in going in over here. So because we're looking at a device like this, we call them ratiometric, we'd actually say that the output is proportional to the input only when we divide it by the input voltage. So if we say Tx here, we're more correct in saying this is input, and then we say gain is what we are looking at the output. Okay, so gain out, which is G is equal to V out divided by V in. Now this is a really important quantity to care, or a really important property to care about. So this means that if we change our supply voltage to one of these devices, we change our output. So let's have a look at a circuit if we were calibrating a pressure transducer. Let's change that to a variable power supply. So if we were then looking at the pressure going into this, if we were to look at this on an oscilloscope screen, then we'd be looking at, say, for constant pressure, we'd expect a signal to be somewhere on this screen. Now, if our signal wasn't very visible, one way that we could increase our output is by increasing the input voltage. So let's draw this on here. Let's say this is V1 is our input. If we put it up to V2, which is less than V1, sorry, V2 is bigger than V1, then we could increase our output accordingly. So that means that if we've got a particular transducer and we've calibrated it at 5 volts, so 5 volts being the power supply, or what we call the excitation voltage, what we mean is that if we're going to use this in an experiment, we have to be certain that the excitation voltage for that transducer is exactly the same when we do the experiment. Now that's not often going to happen because we'll be doing it in a different setup. We might have supply voltage fluctuations, or we might want to change our supply voltage to get a particular different scale out of our transducer. So what we more often need to do is take our output and divide it by the input voltage to get the gain across the transducer. So let's summarize some of that here. Let's say best calibration practice. The best thing to do is to non-dimensionalize Okay, so we non-dimensionalize, sorry, not dimensionalize the input, let's non-dimensionalize the output is what I mean here. Okay, before making any calibration calculations. So if we are recording things as we're going along, we say we record a number of readings as we're doing our calibration. We'll measure the inputs, we'll measure the outputs, and we'll measure whatever pressure we're supposed to be recording. So we've got to have some secondary form of pressure measurement there as well, if we were doing this sort of calibration. So our first reading, our supply voltage can be 5.00 volts. Our V out could be 1.01 volts. And the pressure reading might be 0.0, let's call this 102 kilopascals. Okay? These are just numbers, we're not using them for any recording that we're going along. I could then say number 2, my supply voltage might have increased to 5.01. I've then gone to 1.05 and I've gone up to 108 kilopascals. Now the change in the output voltage includes the respective change in these numbers here. So what I would want to do, these are the values that I'm recording during an experiment. I'd want to look at something else. So I'd say my gain, which is equal to V out divided by V in this case, this would be 1.01 divided by 5. And this one over here would be 1.05 divided by 5.01. And we continue this for the experiment, and what we would then end up plotting for our calibration curve, rather than plotting voltage on the vertical axis, we'd say this is pressure divided by pascals, and we'd then have our gain here. So we would plot our data, and then if we were getting the slope of this out, then we would say that once we've actually worked out the calibration curve for this, we'd take our, let's say this is G is equal to P multiplied by K plus C. We've then got our idea of the relationship of this device. We've got the offset and we've got the bit that we care about, which is the calibration gradient. We would then say that our calibration coefficient is the reciprocal of this quantity here. So for this particular device, the units would be pascals on their own. Units pascals, or what you might see being written and what I tend to write myself, I would say the units are pascals per volt per volt. And this is just a shorthand way of saying, okay, I understand these units are pascals because I'm plotting versus gain. But this is showing you that I've non-dimensionalized my input. So I've divided the output voltage that I'm getting by the input voltage. Sometimes what you'll see being written, you'll say that C is equal to, say, 101 pascals per volt at 5 volt excitation. Now that's very similar. That's what you'll often see on provided on calibration certificates. You'll say they specify the calibration voltage at which you've performed it. Now, I prefer to use this method here, and I prefer to present non-dimensional calibration coefficients, because if we look at mains voltage and what we will end up, and what you guys will have done in these experiments so far, if we look at voltage as a function of time, if we take our function generator, or if we take a mains voltage and we take a DC power supply, if we've got a nominal 5 volts here, it's never a straight line. If we zoom in, we've got big fluctuations in our supply voltage. So those fluctuations would then get passed through into the output. And the way that we can avoid doing that is by non-dimensionalizing and plotting gain versus the quantity of interest. So all of this comes down to the fact, or this is all because most transducers we look at are ratiometric. They're ratiometric because they are often just measuring, so they are fancy devices for turning something we care about into a change in resistance. And what that means is that they are dependent on the excitation voltage, and that can change not just from experiment to experiment, but from data point to data point, and if we're recording transient data during the time history of one measurement. So be really careful with this. Now, what does all of this mean? The bit that we've just gone through, and what we're often not taught as undergraduates, all of this that we've just gone through and I've just shown you here is always, no, let's write that in another pen, always record the supply voltage. So if you've got a transducer that requires often they have a range of input tolerances. So a transducer could have, say, from 5 to 16 volts. Record it. Take the input voltage and duplex it off to your data acquisition system, and record it on the same device, if possible, that you're recording your output on as well. That means that will help if we're ratioing them later, if there's some non-unity gain inside our ADC, that will help get rid of that. We're not going to look at that too much for today, but if you take one thing away from this lecture, always record the supply voltage. Now, this is the thing that undergraduates tend not to be very good at. We think, okay, well, I've got a transducer, I've got a black box. In fact, let's put up something green so that's fully black. I've got a transducer and I've put my physical quantity into it. I'm feeding it with the supply voltage. It says to give it 5 volts. I've given it 5 volts, so I can forget about that now. Now, what you think is 5 volts could be 5.01, could be 5.1. Okay, that's a big change. So that would be 5.1, it would be a 2% increase in all of your values from that point onwards. So proselytizing a bit here, but you need to record the supply voltage whenever we're doing any form of experiment with a transducer, and particularly when we're doing a calibration, of course, because we'll use these data for everything else that we do. Okay, so let's do some data reduction with Python. So historically I've used MATLAB with this course. I know that not everyone here has a copy of MATLAB at home, and I know that it's not very easy to use MATLAB on the VCL. So I've taken my time to get a little bit better with Python. I'm hoping that you guys can also take a bit of your time to get a little bit better with Python as well. In fact, let's have a look for some resources. Super easy to find. So let's have a look. I found a free Python tutorial online. Let me just see if I can find that. Hold with me 1 second. Okay, so now we can look at this. I did a search for free Python online courses. I haven't taken this one, I don't know it, but this is a Python core in advance, and it's a way to understand how to do things. Now, a lot of these tutorials online are for people that want to, say, understand how to use Python as coders and developers, and it might be more useful to, say, understand the piece of software that we're going to be using is Spider. So let's have a look for Spider. Have a look for a Spider Python intro course. There's many of them. There's ones at Coursera. There's videos available on YouTube. There's loads that we can look at for using Spider. So I'm going to load that up now. Let's have a look at Python. So this is my Python window. I'm not going to go through everything with how to use this for us. So let's, here we go. There we go. So you might recognize this looks a little bit similar to MATLAB, which is why I like to use Spider. Python is a sort of more, I would say, more grown-up programming language for actual programmers. I like to use Spider because what I can see is I've got something that looks a little bit like MATLAB, which is what's called an integrated development environment. So I can write my code here. I can see my outputs over here. I can see plots, and I've got everything that I want to see. So what I'm going to go through now is I hadn't written any of this until a little bit earlier today. I had to play around with how I do things. So some of this you need to do one of those intro courses on your own if you don't have MATLAB. You can also, by the way, you're free to, for this course, continue to use MATLAB if you have access to it. You'll need to do this data reduction somehow. You can use Python, MATLAB, Excel, R, or Fortran, or whatever you want to use. I'm just trying to give some examples in Python here for those people that are away from being able to use MATLAB on campus or haven't got their own versions. So there's a couple of packages that we always use, or I end up using in Python, and so we import them at the very beginning. So I'm going to import NumPy as NP. This means I can then use all of these inbuilt functions of something called NumPy or NumPy, which gives us a lot of the MATLAB-like familiarity. And then I'm going to import some things to plot with, so matplotlib. If I can type properly. There we go. And I want to introduce something called pyplots. And I'm going to have this as something called PLT. So I can then use PLT to produce things. So if I want to produce a figure, I do plt.figure. And I'm going to just make it the first figure. So if I run this now, it produces a figure in my plots area. Well, it hasn't produced anything because it hasn't plotted on it. But it would be produced up here when we plot on it. So we need to create some random data. So I'm going to create some. So I'm going to put 20 data points. And I'm going to choose I'm going to take equally spaced measurements from 1 to 10. So let's say that. Let's say, I'll say this can be my pressure in. P is equal to, so similar to how in MATLAB we've got linspace, I then use NP because it's an inbuilt part of the NumPy package that I've just imported, so I can then use it. It's a method of NP. So I want to go from 1 to 10, and I want to have n data points. So I can then say here, if I want to look at P, There we go. I've got 1, 2, 10. I've got 20 data points taken here. Okay, so that's good. So I don't need to plot this all the time. I'm then going to say, my random gradient. This is my pressure. I want to look at what my gain is across those. So I'll then say my grad in. This is my gradient that I'm trying to emulate. I'll just call it 3 for the moment. You don't need to end lines with a semicolon like in MATLAB, but you can see for me it's muscle memory to do that because I use MATLAB so much. I'm then going to say that I'm going to produce some data. So I'll say that my gain that I'm getting out is going to be equal to P multiplied by the gradient in. And I'm then going to plot it. So let's try doing this. I'm looking across the code I wrote earlier. I can't remember how to do all of this in Python off the top of my head yet. So we'll say our data is equal to plt.scatter. So plt is what I imported up here, and I can produce a scatter plot. P, G, and I want to have X markers. And this is really handy. I can say I'm going to give this a label, and I'm going to call it data. And this is better than MATLAB because I can say what data is when I'm plotting it, and then the legend can build it in a little bit later. So let's run that and see what I get. Doesn't like that because I haven't put an equal sign there. Okay, it told me invalid syntax, and it tells me where it caught that. So let's run this again. There we go. I've got some data in here. Now, real data isn't ever quite this linear, quite this perfect. So I'm going to add some noise to this data. So I'm going to add np.random.rand, and I'll say I want to add a vector. So I've put equals here. This should have been plus. I'll put a vector that's the same size as my p. So it's got to have 20 points. And I'm going to divide this by 10. So I've got a small amount of... Well, let's keep that where it is at the moment. So if I plot this, it's then overwritten it, and it's then changed my spacing of some of these here. So now what I want to do, let's just make this slightly smaller. Oh, I've put this in the wrong area there. I shouldn't have made my P bigger. I should have made G bigger. Okay, so because this is just spaced out my measurements. What I wanted to do, I wanted to see variation up and down here. So let's change that. There we go. So we've now got some variation in these data. It's all got my existing plots here. I can't figure out how to close these using the console or writing in here. So what I can do up here, I can just do close all. If I run this, here we go. I see my data, my fake data looking pretty data-like. So let's give these a title, and I'm just going to copy these lines in. Okay, so I can give it a title, plot of P versus G. That should actually be G versus P, shouldn't it? And give it an X label and a Y label. Obviously, we're going to say this has got units of pascals, and then G is unitless. Run this. Here we go. I've got a graph that looks pretty good. Now, what I want to be able to do is fit a line of best fit through this. So if we know that it's going to be a linear calibration curve, because I said earlier we need to have an idea of what our transducer does before we use it, I then can fit a line of best fit. I'll fit a polynomial of order 1. So fit a line of best fit through this. I'm going to say pfit. This is very similar to polyfit from MATLAB again. But remember, I can't just use polyfit, because if I try this, it doesn't know what it is. I have to do np.polyfit. This is because I imported numpy, and I can then use polyfit there. So pg1. So my x data is p, all of these p points. My g data is the g, and I want it to be of order 1, meaning that I'm going to get 2 parts out of it, one of which is my linear relationship, and the second of which is my offset. So if we go back to this curve over here, let's have a look. The bits that I'm going to get out are, what we're expecting to see is I'm getting my 2 parts of my polynomial curve out. The first bit is going to be my k, the second bit will be the c. So I'm producing a curve that looks something like this. So going back to Python, let's plot that. Let's see what I've got. So mp.polyfit, here we go. So I've got that out. I can't do anything with it yet. So let's see what pfit actually is. There we go. I've got a gradient out that's 3, and I've got an offset of 0.24, meaning it crosses at 0.24, and it's a gradient of about 3, which is close to what we get here. So that's good. So I'm going to then say I want to plot a line from my very first to my very end with this gradient and this offset through. So let's make a 2-element array. So in MATLAB, I just put square brackets around it, but in Python, I need to tell it to make a NumPy array. I'm going to say P, and I want the minimum. And I want to go to the maximum of my P vector. Now let's just check what this gives me. This should give me a 2-element array, yeah, from 1 to 10. I could have just written that up here, but what this enables me to do, this enables me to change my input up here. Let's say I want to go from 1 to 19.69. Okay, doesn't change anything down here, and it just means that I want to plot my calibration curve from 1 to whatever my maximum was. So then that's my P plot. I now need to then make a G vector, a gain vector showing what my line of best fit is going to look like. So I'm going to do P plots multiplied by, remember when I got my, let's just do pfit again. So pfit is my line of best fit. Remember, this is my gradient, this is my offset. So gplots, I want that to be equal to pplots multiplied by that first element of my bit that I just got out here of that line of best fit. Now the first element in Python, it's what's called a zero index language, meaning that the first element is actually 0. So I then write pfit, and I use square brackets to say where I am in the array, and then I'm going to add on pfit the second part, which is actually number 1. Okay, I'm then going to draw a graph onto here, so I'm going to say plt.plot. So rather than doing scatter, I'm going to call it linfit. I don't necessarily need to give them names, but I like giving my plots names because it helps me a little bit later. So I'm going to pop pplots, which is the bit that I just made, gplots, and I then want it to have a red line, and I'm going to give it a label. So let's try running this, see if it works. Label's not defined because I didn't give it an equal sign. That's why. There we go. So I've got my plot here, I've got my line of best fit on, and I can just do a legend on here as well. So plt.legend. Because I've already given these two the names, linear fit and data, that's really useful. So that's helpful for us. Now, I'm printing that pfit array because that's what we want as the output from our calibration, but I'm not printing it in a useful way. So what Python's really good at is handling strings by comparison to MATLAB. So I'm going to say print the calibration curve. So I'm going to do print, and I want to say the calibration curve is, I'm going to say it's going to be G is equal to, and I'm going to print to 3 decimal places. It's going to be equal to our gradient multiplied by P plus 1.3 plus the offset there. And then I need to give this 2 numbers. So I'll say this is pfit 0, pfit 1 there. Will that work? Let's give this a go. Doesn't like that. Why doesn't it like that? Oh, it's because I've given this percentage symbols there. I don't need to do those. These should be Fs, sorry. This is saying I want fixed precision. I've doubled up on those percentage symbols there. There we go. The calibration curve is 3.00p plus 0.468. Now it would be useful to have this in this curve up here, so I can then just take these line that I just plotted here and I can pop that into my curve here. So let's take that. Let's just check if this works. There we go. Okay, so the data's random each time, so it's come up slightly differently. I've then got my calibration curve out. Now, the calibration coefficient is not this thing here. It's 1 over this part that we have. We've got to be careful about this zero offset here. We need to make sure we record it. We don't necessarily use it during our experiment. We just have to make sure that we're aware of what this value is and check if what we count as 0 during our experiment is too far from this or not. So we can then just also print our calibration coefficients. So let's try this. So I'm going to, at the end of this, I should be getting out something like 1 over 3 here. There we go. So the calibration curve is given, and my calibration coefficient is also given here, and I've given some units for it. So none of this was particularly difficult in the way that we went through that data processing using Python. This would be super easy to do in MATLAB if you've got a copy of it. I advise you guys, whilst you've got a bit of time at home, I know not everyone's super free, not everyone's got lots of free time compared to normal, but quite a lot of you will be. You'll be stuck inside playing video games, watching Netflix, trying not to get annoyed at your significant others or family. If you've got some free time, it's probably a good idea to pick up another programming language, because as engineers, we're always going to be writing computer code to do things that we don't want to do. So now would be a good chance to go to some of those coding websites and resources and see if you can pick up another language like Python. I'm going to start doing more examples using Python in class for a couple of reasons, because as I've said, it helps you guys who haven't got MATLAB at home do this for free. Secondly, I want to learn Python better than I already know it. So I taught myself how to do this plotting this morning. I use Python for a lot of data processing without plotting at the moment, so this was all new to me this morning. There might be some better ways of doing things. If there are, put it on Slack. Talk to each other, help each other find out how to go through it. Okay, so let's go back to the Blackboard now. So we've gone through the data reduction with Python. I'm not going to upload that simple script to Blackboard or anywhere. You guys can sit there and type those commands in, but remember, what you want to look for is if you don't have a version of Python already, get the Anaconda distribution, and then the software or the IDE that I was looking at. Remember IDE, which is Integrated Development Environment. That is called Spider. Now Spider is useful because it helps us write pieces of code like that. What is also useful is, and let me see if I've got a copy of this open anywhere. I don't, annoyingly. I can show you another. I will bring this up. Just give me one moment. Let's launch Jupyter Notebook. Some of you guys might have used Jupyter Notebooks already, so let's bring up one of those. Jupyter Notebooks are really useful because they enable us to have a mixture of images, LaTeX formatted text, and then code to give you outputs. So you can do some of this stuff in MATLAB using live scripts again, but the reason I'm teaching it here is using the and the reason I'm doing it in Python is just because you guys can again do this at home. So I'm going to let this piece of code run, and then I will give you guys a look to it. So let me just switch to that video. I'm recording this on a very cool piece of software that enables me to capture lots of different things at once. Anytime I want to capture a new window or a new, say a new Safari tab, I have to then add this as a new separate source. So that's why this takes a little moment to go through. Now, this here is, let me zoom in on it, is an example of, I can put code in here and I can then produce a problem with mixed text, and then I can run pieces of code and it gives me the output here and I can format it correctly. So I will end up giving this to my other class, but this is the general solutions for one of the homeworks. So I think there's a couple of people in this class who are in both. You'll be receiving this anyway. But this piece of code is great because I can like I say, I include a mixture of figures that I've just taken from elsewhere. I made this myself, and then include LaTeX formatted equations, and then I can put some code in to get some answers out. And that's incredibly useful. And we might start using some more of this as this course goes on, just to help us understand different processes that we're doing. So have a look at that. Now, Spider was the bit that we were using. What we just looked at there was Jupyter Labs. Okay, Jupyter is spelled with a Y, Jupyter. So I'm not going to talk any more about Python now. Try and look at it if you can. If you want to use MATLAB, that's fine. If you want to use Excel, you can probably get away with that for this course, considering what we've got left to do. But if you want to be a functional and good engineer, you should try pick up a couple of other programming languages. Homework. So for this week, you've got to be able to reproduce the procedure completed in Python with other data. So have a look at what I've done. Check that you can do that. You can, even though I say completed in Python, I mean the bit that we just did in Python. So you can choose the programming language. So if you want to do it in MATLAB, do it in MATLAB. If you want to do it in Java, do it in Java, C, Fortran if you happen to be 50 years old. You can do it whatever you want. Now, I say do it with other data. I've given you a procedure to do it with random data there. So if you can do that, you'll be able to do it with anything else. And we'll start looking at how we get data in and out of Python. We already know how to do that in MATLAB because I've given you different means of doing that. So we're going to try and look at other ways we can do that using Python. There's no assessment this week, but there will be a calibration exercise, date TBC. This will be loosely based around what you would have done for the first laboratory. So it's taking data, coming up with a calibration curve, and then talking about the uncertainty about that calibration and how uncertainty is propagated through the system. What are we going to talk about in our next lecture? So that part that I spoke about, uncertainty measurement and graphical representation, how we can plot that. So if I've got my plots, and I've got these data points, how do I measure suitable measurements such that I can put these uncertainty bounds on in both directions? So we're going to talk about how we can do that with measured data. We're going to talk about firstly how we get these uncertainties. So how do we get those uncertainties? So it's not just a case of measuring the uncertainty in data we've taken. We've got to think about other sources. So other sources of uncertainty that we can have, we've spoken a little bit about them before. We've got things like if we've got an ADC, we're using an analog to digital converter, then we've got a sensitivity. Sorry, I don't mean sensitivity, I mean resolution. Again, we remember that the resolution is going to be equal to the input range divided by 2 to the power of n, where n is the bit count of our ADC. So we got to include that in our uncertainty measurements. And then also we can think about other sources of let's put this up here. Other sources of uncertainty. Say if we've got any constants that we might use. One we often use is G. What do we think G is? Well, if we're mechanical engineers here, so we're thinking G is normally 9.81 meters per second squared. If you guys were aerospace engineers, you'd be taught to use 9.80665 meters per second squared. That's what we agree upon as the value. If you're in high school, it's maybe 10. G actually depends where we are on the Earth's surface. So I think G for Chicago, from the top of my head, is about 9.803, I think. You guys might want to check that. Someone Google that. Find out for me what G is for Chicago and put it on the Slack space so we can find out. But the fact that these things change where we are in terms of the Earth, or the fact that we also can't necessarily write this out to an infinite number of decimal places, means there's uncertainty in constants we use. So because we've got these different sources of uncertainty, what we've got to look at is the propagation of uncertainty. So we're looking not just at how, if we took some measurements, how good was our transducer at measuring those raw things themselves. We're looking at how good was our ADC, what was the resolution of them. If we're taking those data points and we say if we were measuring pressure but we're then converting it to velocity, what constants do we use to get from those? So one of them would be gravity and part of the calibration perhaps. Another one would be, say, the density. If we're measuring a density, how precisely do we know that to? And then we look at the uncertainty there. We can propagate these through using standard propagation of uncertainty procedures that we'll go over next week, how they feed into our final result. And what we end up with is what's our final uncertainty. Okay, so then when we've got those measurements, we pop them on our graph. We say we think the result's here in the middle, but it could be anywhere within these bounds. And so we're going to use some statistical analysis, looking at things like the standard deviation, and then we'll look at how errors are propagated through, and we'll do some partial derivatives to see how those work. So that will be next lecture. We're going to do some more examples of calibration produced with some real data, and then we can talk about them, whether they are valid or not, and how we can use them. And I'm going to give you an introduction to the calibration homework that you guys will be receiving. So that will be coming up in the next lecture. So that's all we've got in terms of the raw content today. So let's just talk a little bit about what we've done. So we've covered a lot of things today. We covered the administration of this course, how it's going to go moving forward. It is going to be I don't want to say making it up as I go along. I promise you I'm not just doing that. I'm trying to give you guys the correct and most useful learning experiences that I can, constrained to the environment in which we are. So there'll be a certain element of giving you videos talking about measurement, and then giving you data to do some analyses yourself. And I appreciate you guys bearing with me as we're going through this, because I've got to run some of this by my departmental colleagues. I've got to get in some disagreements with some of them about quite what I should be teaching. And as I say, I very much appreciate you guys bearing with me as I'm doing this, because I'm learning new things as I'm going along. And it's not just stuff like figuring out how to use a green screen, although that is kind of cool. I think this is pretty fun to be using. So that's really appreciated. We've gone through that. You've got to watch all these videos, you've got to do all the quizzes, and you've got to pay attention to Slack to look at when homeworks are coming out. So make sure those are being done moving forward. Go through and understand what calibration is. If there are any questions, you know where to put them on the Slack space, and I will answer them as we come around to it. I will be figuring out how to do an office hours session. I think we'll probably be using Blackboard Calibrate. Some of my colleagues have had some successes with it. Some of them haven't done quite so well. Sorry, not that they haven't done so well. Some of them haven't managed to get it to work properly, because I think Blackboard's not always the most user-friendly piece of software, so we'll figure out how to do that. I will make an announcement on Slack, and I'll probably send an email as well just to catch anyone that's not using the Slack space yet. So that's about it for me this week. I sort of feel like I want to say like and subscribe here, but I'm obviously not an actual YouTuber. Please make sure you ask questions as we're going along. If you need to, wash your hands. Not that I'm in any position to give medical advice. And try and stay sane during this downtime. Okay, have a great week and weekend, guys. I will speak to you all next week.